Welcome to Module 204D on protection devices. Within this module, we have 6 different objectives we need to cover, and we're going to break this into 2 different videos. So the first video will be covering objectives 1, 2, and 3, and the second video will be covering objectives 4, 5, and 6. We'll get started by looking at the basic overcurrent and overload protection devices that we have available to us for our circuitry. Before we talk about the devices that protect our circuits, we have to look at what we're protecting our circuits from. First, we have an overcurrent condition. An overcurrent condition is any condition in which we exceed the limitations of the circuit's ampacity. Normally, we see an overcurrent as being a short circuit or short to ground. So anytime I go between line to line to neutral, or line to ground, could be an overcurrent condition. What we would expect with an overcurrent condition is a rapid, sudden increase in current to the point where it exceeds my protective device. The other condition that we have is an overload condition, in which case we're just putting too much strain and too much load on our motors. What results is that the motor will start pulling more and more ampacity until it can overcome that load. As a result, we could experience things such as coil burnout or wire burnout of our motor. Each of these conditions have devices that can help protect our circuit against it. In the case of an overcurrent or a short circuit, we would use either breaker or fuse. And the idea behind this is that we'd have that rapid current buildup that we have with a short circuit, which would take out the filament inside the fuse, or it would exceed the limitations of the breaker, and it would automatically disconnect the circuit. To better understand these devices, we're going to take a look at their construction. A fuse is a fairly simple device. It is meant to protect against short circuit or overcurrent conditions, and it has a small filament on the inside of it that will melt when a certain temperature has been reached. The basic construction of any fuse is the same. We have 3 different components that go into making this up. First, on the inside we have our element, which is the heat-sensitive conductor that will melt when a certain current value has been exceeded. Around the element, we have an arc quenching film material, which could be air in some cases, and around all that, we have the enclosing body. We will use different styles depending on the application that we have. A fuse has 2 functions it must meet. First, it must allow the circuit to function normally without any deterioration. So this is its passive function. It just needs to work as a conductor and allow things to operate. Secondly, it must open the circuit under abnormal conditions, and this is the active function. So anytime I have a short circuit condition, we want that element to open up and therefore stop the circuit from operating. And there's 2 different types of fuses that we can use. The one you see on the screen right now is called a non-time delay, which is a single element fuse, and it will interrupt current immediately on an overcurrent condition. In some cases, we would want to have a time delay fuse, which is a dual element fuse. Some equipment has a very high momentary inrush of current, such as motors and transformers and capacitor banks. So therefore, the time delay will prevent any nuisance tripping for these items. If the current remains high, then the fuse will still open. The 2 elements that we have within the time delay fuse are our short circuit element and our thermal cutout element. The short circuit element is sized to handle any inrush of current, but it will open if current goes above inrush rating. If we were to compare the time delay short circuit element with the non-time delay element, we'd find that the time delay short circuit element is very large compared to the same size of fuse on a non-time delay. The reason for this is that we want that extra capacity to allow everything to start normally. But when we have a short circuit condition, we'd have a very sudden and drastic rise in current, and that's when the short circuit element is going to open up. Our second element is our overload element, or our thermal cutout. The thermal cutout will protect the motor from a prolonged high current. If there's not enough current to trip out the short circuit element, but there is enough current still there to damage the motor, that's when the thermal cutout will open. It has inverse time characteristics, which means that the higher the overload current, the faster the fuse opens. So it provides a delayed response up to about 500% of the fuse continuous rating. So with my time delay fuse, I not only have overcurrent protection, but I also have overload protection. The other type of overcurrent protection I have is my circuit breaker, and they've been built with a very unique mechanism called the trip-free mechanism. What this means is that with my circuit breaker, even if I held the handle in the on position, if I exceed the current rating of the breaker, it will still trip the internal mechanisms regardless of the handle position. Some manufacturers have built in an indicator that will tell you whether or not a circuit has been tripped or if it is operating normally. There are two different types of circuit breakers that we are able to buy. First of all, we have the instantaneous circuit breaker, which only protects against a short circuit condition. And it's a very specialized breaker that's normally used only for motor circuits. We use this in a circuit with some other type of overload protection. The other type of breaker, and it is the most common type that we have, is called the time limit breaker or the thermal magnetic circuit breaker. The time limit breaker is a code term that we use for table 29 when we start talking about sizing different types of breakers. This type of breaker not only protects against short circuit conditions, but it will also protect against any overload conditions. And it uses a bimetal strip for time delay tripping, and it uses an electromagnetic trip element for instantaneous reaction. When it comes to my motor circuits, I need to have two different types of protection in place. I need to be able to protect from a short circuit condition, for which I will typically use an instantaneous breaker. And then I also need to protect from an overload condition, which is generally a separate device that we'll find on a motor starter. There are two different types of overloads that I can use as well. Typically, we would have what is called thermal overloads, which operate by detecting the heat within the circuit, but we can also use magnetic flux overloads as well, which are a solid state device. Now that we've had a basic overview of our protective devices, we're going to look a little bit deeper at the characteristics of fuses and breakers. If we are going to use a fuse in order to protect our circuit, we first must decide what kind of loads are in our circuit to protect in the first place. We have a choice between using non-time delay and time delay fuses. For our non-time delay fuse, we would use this in such circuits such as electronics and most common circuits that we have. Anything where we do not have an inrush current that we need to worry about, and we simply want to protect our circuit from an overcurrent situation. For our time delay fuses, these are also called anti-surge fuses. And these are used when overcurrent conditions can exist under a normal circumstance, such as when motors draw a larger than normal current when they first start up, but the current will drop off once the motor gets up to speed. To understand the reason of why we would use a time delay fuse with a motor, let's look at the current profile on startup. When I initially energize my motor, the windings inside basically act as a short circuit because I have no inductance yet. So therefore my total impedance is no more than my resistance, which means I have a very high maximum starting current. As the rotor starts to turn inside the motor, we start to build up my impedance, and therefore my current is starting to drop off. And the faster my rotor goes, the lower my current is going to go. So when my motor reaches full speed, I should be slightly under what the rated current of the motor is. But it is that initial bump as soon as I energize the circuit that causes problems within the circuit if I have my fuse ratings too low or if I do not use a time delay fuse. That bump might only exist for a fraction of a second, but that fraction of a second is enough to blow most standard non-time delay fuses. In order to select the proper fuse size for my motor circuits, I'm going to look at Rule 28200. Subrule 3 states the rating of the overcurrent device required by Subrule 1 shall not exceed the values given in Table 29. So Table 29 shows us what we can select for our fuses. It will depend on the type of motor that we're using, and it also depends on what type of protection that we're using. For example, for a squirrel cage single-phase motor, if I use a time delay fuse, I can go up to 175% of my full load current. If my full load current, for example, is 10 amps, I could go up to 17.5 amps. If I was to use a non-time delay fuse, I would go up to 300% of the full load current. Therefore, my 10 amp motor would require a 30 amp non-time delay fuse, and that's there to allow for that big bump at the very beginning of my start cycle for my motor. When it comes to my circuit breakers, they all have the same type of internal mechanisms, and we're going to look at both the instantaneous circuit breaker and the difference between that one and a thermomagnetic circuit breaker. First, we'll look at the instantaneous circuit breaker. This type of breaker uses an electromagnetic trip element for an instantaneous reaction. It reacts to the increased magnetic field around the conductors due to the rapidly increasing current. The electromagnet then pulls away from the catch, which releases and opens the contacts. The breaker needs to be in a fully off position again in order to reset the catch. But once the catch is reset, it can be turned on again and the contacts will close. We use this typically in motor control applications because it is very precise, it has a very high speed trip, it is sensitive to low overcurrent, and it is not affected by the ambient temperature. Thermomagnetic circuit breakers are the most common type of circuit breakers that we have, and we use them in about 99% of our circuits. Essentially, every circuit that we have that's not a motor circuit would have a thermomagnetic circuit breaker. The thermomagnetic circuit breaker protects against both short circuits and against overload conditions, so it's triggered either thermally or electromagnetically. So we do have our electromagnetic catch the same as we had with our instantaneous breaker, but next to that we also have a bimetallic strip that works on the heat being created by the actual circuit. The bimetallic strip will heat up whenever we have an overcurrent condition, so we're holding the current for too long of a duration, and as that bimetallic strip will heat up, it'll change form and it will allow the catch to release. In Blackboard, I'm going to put a link to this video for more perception. It gives you great insight about how the internal workings of a circuit breaker are operating, and it will show you not only the instantaneous strip feature, but the thermal feature as well. So make sure you take a minute to watch this video. It's very entertaining. However, I warn you, don't do what he does. One of the things we need to be aware of when we're talking about short circuits and the interrupt rating is the fact that my short circuit, since it has no impedance, can go up to an extremely high current value very quickly. So we're going to look at all the different factors that will determine what that short circuit current is going to be. Both my breakers and my fuses have two different values. The first value is the continuous rating, which is the rating at which that breaker or fuse can normally operate for long term. This is a 15 amp breaker, which means if this is rated at 100% operation, I could handle 15 amps on here indefinitely. If this is not rated for continuous operation, I can handle 80% of the continuous, which is 12 amps continuously. The other rating that we have is the interrupt rating. The interrupt rating is the rating I have in which I can safely interrupt a fault current within the system. And this is based on the system properties itself and how much current could rise before the breaker or the fuse will open. And this is the capacity of a device to safely open a faulted circuit without either welding the contacts or exploding. Both circuit breakers and fuses will have interrupt ratings, and we need to make sure that we select the right device for the job. And anytime that we are exchanging fuses or breakers out on a job site, this is one of the values that we want to check. If we don't, we could have a serious problem. The interrupt rating of our devices should be above the fault current that we could have inside our system. And the fault current is going to depend on a number of different factors, such as what the circuit voltage is, what the short circuit path impedance is, and we need to consider both the resistance, the capacitance, and the inductance of the whole circuit path under fault as a total system. But we also need to know what the kVA rating of the supply transformer and what the percent impedance of the transformer is as well. Keep in mind that the location of the overcurrent device to where the fault is also affects what that interruption capacity is going to be. So it all starts with the values that we find inside our transformer. We need to remember that a transformer is limited between its input and output. So whatever the kVA rating of the transformer is, if it exceeds that, it's going to trip out the overcurrent devices for the actual transformer. However, the limitation that we have is whatever the kVA rating on our primary or our input to our transformer is going to be exactly the same kVA rating that we're going to have on our output as well. Since this number is related, we can also apply this to our theory based on our transformer understanding. In order to figure out what my interrupt rating is going to be, first thing I need to do is I need to find out what the percent IZ rating is, which is the impedance rating of inside the transformer. And to do this, I do a transformer short circuit test. Percent IZ refers to the percentage impedance of the transformer. So really, What is the percentage of applied voltage I can put onto my primary coil compared to what the rated voltage of my primary is in order to make enough current flow on my secondary side to match what the rated secondary current is going to be. And we can use the percentage Z in order to figure out my fault current as well. Normally, this is done by engineers and we don't need to worry about it. However, you do need to be aware of it so you can understand the process. The first thing we want to do is find out what our rated secondary current value is going to be. We have a 12,000 VAC transformer primary rated at 120 kVA. If we take that 120 kVA and apply it to my secondary side of 600 volts, we find that we have a rated secondary current of 200 amps. The next thing I want to do is I want to make sure I have no energy on the primary side. I want to completely isolate that transformer, and once that's done, I'm going to short out the secondary winding. This isn't dangerous because since I have nothing on the primary side, there is no current running on the secondary side, so shorting out the terminals is not at all dangerous. The third step is to take a variable transformer and start at 0 volts and slowly apply voltage to the primary side, in this case to my 12,000 volt side. When I read 200 amps on my secondary side, I want to take note of what the voltage level is that I've applied to the primary. This gives me my percentage IZ. So the applied voltage that I have on my variable transformer, that gives me the rated current on my secondary side, divided by the rated voltage of my primary side. In this case, I applied 240 volts to my primary side, which caused 200 amps of current to flow on my secondary side. Therefore, if I took 240 volts divided by 12,000 volts, I find that application of 2% of the voltage on the primary side caused enough current to run on the secondary side to meet the rated current value. How this applies to my short circuit current is this way. My interrupt rating is my rated current divided by my percent IZ. So if I have my 200 amps and I divide that by 2%, I get an interrupt rating of 10,000 amps as an absolute minimum. That means that if I applied full voltage to my primary side and I had a short circuit on my secondary side, I could expect a total current of 10,000 amps to run on that secondary side. Of course, this will only happen for a period of time before the entire thing blows out, but it will occur. My interrupt rating on my breakers and fuses must exceed this value. So I must have an interrupt rating higher than 10,000 amps in order to properly protect my devices. You've now reached the end of the first part of 204D, and I know we've covered a lot of different things in objectives 1 to 3. So make sure you are familiar with the construction of both fuses and breakers and what the difference is between my instantaneous trip and my time delay trip on both of those devices. And also make sure you are comfortable with the concept of the interrupt rating of my breakers and fuses and you understand what that is. It is not important for you to be able to do the percentage Z calculation, but it is important for you to understand why they do it. Once you're comfortable with this information, return to Blackboard and continue on to 204D Part 2.